Okay. So before the break, we ended with this nice sophisticated scheme according to Heun, where we take an approximation, and actually the approximation step, this y star, is just an Euler step, and that's very simple. Oh yeah, you want an image, right? Image? No? Why not? Oh, that's strange. Okay. So before the break we looked at Heun's method, a more refined method. But if you look at Heun's method, we see when we explain it that... Oh, my calendar, yeah. Oh, that's well interesting, huh? By the way, my calendar is also available online, so if you want to know where I am, what I'm doing, or if I'm available for talking to you, look in my calendar and send me an email. This is also not good. This is better, right? Okay, well, third time lucky, right? Re-rep. So before the coffee break, we looked at this scheme, Heun scheme, which is more refined, in the sense that we see it takes the change of derivative, so the curvature, or in terms of, it takes acceleration, change of curvature, change of speed into account. But if you look at the scheme, I don't see any second order thing, calculation. I only see two steps. First, like an Euler step, and then that approximation is used to evaluate again a derivative, and then in some magical way we do like a higher order approximation. And because you could say, if you take this simple Euler step, like yn plus 1 is equal yn plus hf tn yn plus order h squared. That is the idea from the Taylor expansion. And apparently if we do this Heun thing, then the answer here, so let's call this y star, yn plus 1, and this was yn, h over 2, and then we take the derivative at tn yn, plus the derivative at tn plus 1, yn plus 1 star, because that's an approximation. But apparently it will be order h to the power 3 in some magical way. Okay, how does that work? So apparently it's more accurate. This Heun is more accurate. More accurate. That is what we see. And why is it more accurate? Because what we call here is a local truncation error. Local truncation error. And I usually write that as epsilon. In taking this finite number of steps, either Euler or Heun, we cut off our Taylor expansion. We throw away higher order terms. And what is the local truncation error in the Euler method? Well, that's very simple. It's of the order h squared, because we take this simple linear step, and then all stuff h squared and higher is gone. And in the case of Heun, what is then the truncation error? Well, apparently it's a little bit better. It's a third order thing which we throw away. So it's more accurate. Now, this is all very nice, and it gives you the idea that if you refine your step size, that things will get more accurate. But there is one little problem, and that is we are not interested in a local truncation error. We are interested in a global error. And the global error is the sum of all the local errors. And how big is this sum? How many times do we have to sum? Well, let's suppose we want to know our end time. At our end time is a capital T. We want to know a solution at T is, give me some number, 3 seconds, whatever. If you then take a step size h, then the sum, the number of steps you have to take, number of steps, is this t divided by h. So n, oh, my h's and n's are almost alike. Oh, that is not so nice. Not so nice. So number of steps n equals t divided by this step size h. Meaning that it's all very nice to take smaller steps, but then you have to take more steps. So you add up more errors. So it looks as if things are getting worse. Is that true? No, not really, because the global error is very simple. It's this n, so approximately n times this local error. And how do we write global error? Capital E. Capital E, I usually use. So E, global error, is approximately n times this local error. Sometimes errors cancel out a little bit, but we want to be on the negative side, or the what is it? Conservative side, actually, not negative. Conservative side. So then if we look at the global error for Euler, the global error is simply n times this, but n is t over h, so it will be order h. And for Hoyne, the global error after the fixed is h squared. So still sounds good, but it shows that this order is probably not so fast converging, and this is like a quadratic process. If you do step refinement, you expect that your global error will go down in a quadratic sense. So that is very good news, actually. So it means that you can get any accuracy. You can get any accuracy you want. So if you say, well, I want to know to 10 to the minus 3, no problem. You just calculate and recalculate until you see, oh yeah, it's now approximately accurate until 10 to the minus 3. Just by doing step refinement. What do we do in practice? So in practice, we want to know practice. We can estimate our error. And how do we estimate that? Our error. And then I mean global error. Yeah. Global error. How do we estimate that? Well, we know that if we calculate something at some finite time, then at that time, let's put a capital T, I write it once and then I'll drop it. That is the true value. So this is the true value. We don't know the true value, but plus some error. And the error is, well, order h to the power of something, p, and p depends on the method. And since it's order, well, we have some constant here, c1. So this should be approximately how the solution behaves. So the solution we found, this is the solution from the numerical integration scheme, is the true solution, the true value plus some error. And then, of course, this p for Euler, the p is 1, and for Hoyne, the p is 2, and for any other method, there are different values of p. Now, how do you estimate now what your global error is? Well, first you integrate with some step size. Integrate with step size h. Just pick some step size which you think, well, that's pretty okay. And then you find a solution which we call yh. Then second, you do it again, you integrate, but now you use a smaller step size. So we take step size h over 2. And then again you find an answer, which we call yh over 2. The next step is, of course, that you're going to compare the results. So what you know is, well, the y for my step size h is my true value plus c1 h to the power p, right? And then my solution h over 2 is, well, still the true value, plus approximately this constant, the constant probably will not change so much, and then h over 2 to the power p. Now we see here we have two equations and two unknowns. And the unknowns are y hat and c1. Now we're not so interested in c1, but we are interested in y hat. Unfortunately, the plus here is like a plus minus. It's not really a plus. The error can be a little bit up or down. And that makes the solution a bit different. But from these you can actually solve. And we can make an estimate on the global error. So we can estimate the error. I would say global error, I should say. Global error E. And how do we do that? Well, from these two equations we can say, well, apparently the global error is this y hat minus the y, and then we take the most accurate result. We can say, what are they approximately? Well, it's 1 over 2 to the power 2p minus 1 times y h over 2 minus yh. So that gives us a bound for the global error. This is just simply the solution of these two equations. Not simply, because we have the plus minus, so the only thing we can say is about the error we have. It should also be like the absolute value. Now it's all very nice, equations and so on, but this is actually what you do in an intuitive way, right? Forget about this constant. I mean, suppose p is 1, then this constant value was t, then this factor is 1, and for p is 2, we get 2 to 4 minus 1 over 3. So this is just some number, not so super important. It depends on the method, but this is an interesting thing, because this is actually what you do intuitively. You take a step size, you calculate a value, and then you write down the number. For instance, the number you get for the h, yh is 3.15678. Okay. And then if you do, you get 3.149152. And then intuitively, you look at these digits, right? And you say, when do they still change? Well, the first digit is constant, doesn't change. The second doesn't change either. The third changes, but yeah, it is either a 6 or a 5, right? And that's actually what this statement here says, that you compare the two differences, you take the difference times some constant, and that's your estimate for your error. That's a very practical way to do. Now this is accuracy for our method, and but there is a far more important thing. So this was accuracy, and you can accuracy. Far more important is what we call stability. And what do we mean with stability? Yeah, it means like the thing, if you have done a felony or something, you go to court and you have to go to jail. But then after a number of years, you're released. So your whole history about being bad is gone, and you're good again. And that's a bit the problem here. You make errors, right? And people make errors in life. And numerical schemes also make errors. Every time you take a step, you have a truncation error. Now suppose that this error gets amplified. So you start with a small error, and then you take the next step, and then the error from the previous step becomes a little bit bigger. And then you take the next step, and then that error which you made like in the beginning becomes bigger and bigger and bigger. That's the same thing as like having been in jail and then being never released, right? And you don't want that. So we want to forgive. So we want to know, and that has to do with the method. Is this method forgiving for errors made in the past? So can I start a new life? That is the big question. Does this method give me the opportunity to start a new life, to start afresh? Now, how do we investigate the propagation of errors? So that is propagation of errors. We need a test equation. We need a test equation to test our method. And the test equation we use, we need a differential equation. And the test equation I propose is y dot is lambda times y. I find that one of the most beautiful test equations. Why? What is the beauty of this test equation? Do we know the solution for this test equation? Yeah, you looked into your lookup table and you found? Yeah, everybody knows, huh? Everybody knows that the solution is y of t is e to the power lambda t. Yeah, and then maybe even times a constant, some constant, c times. This is a general solution. Now you would say, well, that is rather restrictive when we take as a test equation the exponential function, because then the only thing you can have is either it goes like this for lambda being negative, or it goes like this for lambda being positive. So we have either an exponential growing function or exponentially decaying function. And that is sort of boring, right? True or not? Not true? It's not boring? You don't care? Well, I find it too restrictive. I mean, in dynamics we do not have problems which are either decaying or exponentially growing. Maybe in cell biology, but I'm not a cell biologist. My son is. So why is still a function very nice? When you don't know, there's one thing you always have to remember, and that is the following name. Euler did it all. Euler is the genius, right? Why Euler? Well, suppose that this lambda can be also not real, but also complex. Why not? Yeah, we do complex multibody systems, so we use complex numbers. And what happens if you do e to the power a plus bi t? You get a to the power et times a to the power bit. Well, this is just either, if it's positive it's growing, if it's negative it's decaying, but what is this complex thing? Yeah, this always moves in a circle. Or in other words, I can write this as a, yeah, what what did Euler say? Cosine bt plus I sine bt, right? Wow. So now what do I have? I have either growing or decaying, and I have oscillatory. So I have either this, z, z, times, and then solutions like this. Or in the end, I have either this, no, oh, that's okay, growing, or something which is decaying. Or maybe an intermediate one is always zooming along. Which is pretty neat because that encompasses almost all solutions in our motional multibody dynamic systems, right? Yeah, this is with a constant, but not so important. So the test equation is rather neat because it has this whole family of solutions of oscillatory ones, either growing or decaying. So we're happy with that. Now, what do we do with that test equation? Okay, so back to the test equation, and the test equation was set is y dot is lambda. And what do we want to test? Well, after one step, we have that the approximate solution is the true solution plus the error, right? So this is true, this is a prox, and this is the error. Now, how does this evolve? We are interested in how does this evolve for y dot, which is differentiated, true solution dot plus epsilon dot. If we put that into our differential equation, then what we get true y dot plus epsilon dot is lambda times y plus epsilon at, well, of course we can cross out these two, and we get epsilon dot is lambda times epsilon. So the solution, the error behaves exactly the same as the solution behaves. So for error propagation, this is the error propagation. Now, if this this value lambda, so if the real part of this lambda is positive, then the system is stable only on a fixed interval. So stable on fixed interval. And of course you understand that immediately, because if we do an exponential growing system, then of course the errors we make are exponentially growing. So only on a finite interval we can say, well, we can limit the growth by taking smaller steps and adding up these smaller errors. Now, in the case that the real part is less than 0, we say, well, then the system is unconditionally stable system. And then the big question is, does that also hold for the method we apply? So the next step what we do is we take a method. So back to the method. And let's, for Pete's sake, I started here just with Euler. For instance, we start with Euler. And I'm looking at error propagation, so I should write epsilon. So I write epsilon n plus 1 is epsilon n plus h times this differential equation for epsilon. Epsilon n, but that is of course was h times lambda times epsilon n. So this is how the error grows, or behaves actually. Or in other words, we can directly write that the error is 1 plus h lambda times epsilon n. And you have the feeling that, ooh, whatever I do here, it will always be bigger than this one, right? Because it's 1 plus. But hold your horses. This amplification factor, which we should take the absolute value, of course. Yeah, that's right. That's C. Amplification factor is 1 plus h lambda. We have to look at what is this? Is this ever less than 1? And you would think, well, no, never, because it's like 1 plus, right? But lambda can be complex. If you have a pure oscillatory system even, then lambda can be complex. So, for instance, pure oscillatory, I don't want to look at pure oscillatory. Then lambda is plus or minus I omega. And if we have like a damped oscillation, we have lambda is minus beta plus I plus or minus I omega. So this lambda can be some complex number, and if there's little damping, then there's a little real, the real part is little. So to look at this, when is the amplification factor less than 0, or when is it less than 1, or when is it equal to 1, and usually we say, if we are interested in this one, we say, well, when is CH lambda is equal to 1, that is the question, then we know the border. And then we have to substitute values like this lambda. For this lambda, we have to take a complex number, so we say h lambda, for simplicity, is a plus bi. And then we put that in the equation, so we get the absolute value of 1 plus, and then this h lambda thing, h plus bi, when is this 1? Now we have to plot that in the complex plane. So here's the complex plane. So here we have the real part of h lambda. In our case, that's this a, right? And here the imaginary part of this h lambda, and that's our b in this case. And in this complex plane, we want to know where is this border. Now, in this case, it's super simple, because if we take the norm of a complex number, that's like a circle, right? And if we want to know a circle with radius 1, that's just a circle. We forget about the 1. And then, actually, you could say, oh, there's a shifting on the real axis. So it's shifted to the left by 1. So it's like a circle with radius 1, something like this. So this is minus 1 and this is minus 2. And then everything within this circle, all values within this circle, this h lambda, means that is a very stable solution. So all eigenvalues, all these lambdas, h lambdas, which are here, are perfectly good with the Euler scheme. So if you, meaning also this is about h lambda, so you can make your if you have some eigenfrequency of your system, then you just have to take this step size small enough to calculate a stable solution. You have no error propagations. So, now if we look again close to this, then pure oscillatory solutions, lambda is plus or minus I omega, means that h lambda is then plus or minus still I h omega, right? Meaning that everything is on this axis. Now, which value from this axis is within this region? So this is a pure oscillatory system, right? Pure oscillatory system, these are the eigenvalues. H lambda is then just this one. And where is this I h omega? Well, that's on this axis. Not here, not here, always on this axis. Which point from this axis is within this region? 0. Exactly. So we can do a pure oscillatory system, stable, no error propagation, propagation means, well, omega has to be 0, or in other words, it's non-oscillatory. Or, in other words, you cannot integrate an oscillatory system in a stable manner with the Euler method. That's sheer impossible. Doesn't work. So Euler scheme has a disadvantage. It shows this amplification of errors. So if in your ignorance, if you have this simple pendulum, no damping, right? Simple pendulum, no damping. We have this mass here, length, gravity. And then you think, oh, nice, with Euler I can do the numerical integration. Then if you use Euler method, what will be the result? Well, if this is time, and this is the angle, or the displacement, fine, doesn't matter. Then what will you see? Oh, it goes nicely. Hoopla. And even if you do step refinement, it will still nicely. So you have found an infinite source of energy, right? It's a nice way to move a pendulum. Just use Euler's integration scheme. So that doesn't work. So we have to do something else. Well, let's look at Hoyne. In Hoyne we had I should say epsilon now. We're talking about the errors, right? So I should write epsilon. Epsilon star n plus 1 is epsilon n plus. Well, the differential equation was h times epsilon n. That was the approximate. Then the real value, n plus 1, is epsilon n plus h over 2. Then we have the value at the initial one, the derivative, that was h epsilon n, plus the derivative at this point, and that is this I forgot a lambda, right? Yeah. Plus lambda times this value, h lambda times epsilon star. N plus 1. Of course, then I can substitute that in this equation. And then when I expand that, I get epsilon n plus 1 equals, and then I get 1 plus h lambda plus 1/2 h lambda squared times epsilon n. It's just math, just put one in the other and do the calculus. And then you see, so this is now my amplification factor. Amplification. So in other words, I have to assume this h lambda is a plus bi, and I want to draw this in my complex plane. That this amplification factor is less than 1. Now this is a bit more complex, and well, you can do it in MATLAB with contour, and there are all kinds of ways to do that. But the end result looks something like this. Again, here we have the real part, of course, of h lambda, and here the imaginary part of h lambda. Then here this is minus 1, this is minus 2. Oh, that's not a nice minus 2. Minus 2. Then we get a figure something like this, like an oval-shaped thing. And I think, if I remember well, this is square root 2i, and this is minus square root 2i. But still, the circle becomes a bit of an egg, and it's a bit bigger, and so again stable, no error propagation. But pure oscillatory systems still unstable. So for pure oscillatory lambda plus or minus I omega, unstable. So again, if you do with the Hoyne scheme your pendulum, it will grow again. Is there a solution to the problem? Well, there is a scheme which is very useful, and that is a famous scheme which is called RK4. It's a Runge-Kutta 4 scheme. In the book, it explains who is Mr. Rume and who is Mr. Kuta. There are even pictures of them. And it also explains a little bit what the origin of the method comes from. And I'm missing another page. Well, yeah, here. And the Runge-Kutta scheme, I think most of you have already used it in your numerical methods class. It's a four-step method thing, and it just calculates 4 derivatives. And the first derivative is, of course, at t n y n. Just simple, the thing we do also with Euler. But then the second derivative, what we do, is we do it halfway. So we say halfway, and what is the function value halfway? Well, we just take yn plus h over 2 k1. That's an approximate of the value halfway. And then we calculate again halfway what the derivative is. So, but now, instead of using k1, we use this better approximation, k2, h over 2, k2. And then finally, a fourth derivative. That's exactly at the end point. And then we estimate the end point. Well, we take the best derivative we can find, k3 times h. So now we have all these 4 derivatives, and with these 4 derivatives, which sort of express the change in curvature, we can now say, well, the new point is the old point plus h over 6 times k1 plus 2 times k2 plus 2 times k3 plus k4. And if you then look what the truncation error is, that is of the order h to the power. Well, with Euler we took 1 step and you had 2. With Hoyne we took 2 steps and you got 3. Here we take 4 steps, so it must be 5, right? Yeah, 5. So a very accurate scheme, and of course the global truncation error is of the order h to the power 4. If we then look at the stability region, and well, instead of me drawing it, maybe we look, I made very nice pictures actually of those. Yeah. Here we see the stability region. So remember, this was the real part, and z is now h lambda, and imaginary is h lambda. So this is a positive, positive, so I only draw half because it's always symmetric. Then for Euler we had this circle, right? Then for Hoyne we had this egg-shaped thing. Then apparently there's also some intermediate 3-step scheme, RK3. It's in the book, I didn't talk about it. But now look at RK4. So this is RK4, goes like this, and then la 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 la, goes like this. And now I'm very happy because, well, because of course the area is larger, and the stability region is larger. But note that this part of the imaginary axis is within the stability region. So apparently pure oscillatory systems can now be integrated with this RK4 scheme in a stable manner. So there is no error propagation. So errors are sort of damped out into the whole scheme. And of course there are higher order schemes with all their advantages and disadvantages. So this was about error propagation, about different order schemes. Still there's one item left, and that is about the global error. Now, if you now do it in practice, and you make a plot, for instance this, and then here you have the step size h. Oh ja, ik moet dat andere ding doen. Air surfing. So again, global error in practice. So if you have for a certain step size, you can estimate what the global error is, E. So you take some step size, you come up with some approximation. Then you refine your step size, so you go in that direction. This is 0, so h becomes smaller. Then, yeah, you will find a smaller error. And then smaller, and then smaller. And so you hope, of course, that finally you will get 0 errors or small, but then suddenly what happens is this. Ooh, 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 horror. So you took this nice lecture on numerical integration, and then you believed all the stories, and then you thought, oh, if I make it smaller and smaller, things will get better. But then things got worse when you got too small step sizes. So what happens here? Any ideas? What happens in this region? Yeah, you have roundoff errors, and the roundoff errors are actually irrespective of any method. It's just your finite accuracy in the computer. So roundoff errors, which I call then C2, they are, well, if we do double precision in MATLAB, they are of the order 10 to the minus 14 or something like that, right? Some constant number. Depending on the word length used, but let's say it's a small number, so you don't have to bother, but if you take many steps, then your global error will of course become this many steps times C2. And what are the many steps? Well, that was T over H, right? Times C2. This is an H. Meaning that your global error is not what we thought initially, that it was some factor times a to the power p, depending on our method, but we now also have some c2 divided by h. And that is exactly this behavior here. So in practice, what you have to do is you have to stop here. This is the best accuracy you can get. You cannot get it more accurate. And of course it depends also on the method you apply. Now as an example, I want to show you the following thing where it was applied, and that is in this case. So what is this? We call this, let's go back. Can we do it again? So this is the a gibbon which does ape swing. So it grabs onto a handle and then it swings and then it grabs onto the under handle. Now the beauty is he grabs onto the handle with almost zero velocity, so there is no impact. So if you invert the problem, it looks like you're walking without any impacts, right? So, and during the impact you lose energy. So in the case of the gibbon, you probably have no energy loss in this ape swinging. So it's an almost energy conservative system, the ape swinging. And of course you want to know what are the cyclic solutions of this nonlinear dynamic system, because you can model a gibbon as one point mass with massless arms, or you can two pendula or swinging, or 5 pendula. You can make it as complex as you want. And all these systems have cyclic solutions in this energy conservative system. Now, Mario Gomez, together with Andy Ruina, were trying to find these cyclic solutions. And in doing that, I forget about this. And in doing that, they had to be sure that after one period, when their gibbon model grabbed on, that their result was accurate enough to say, okay, this is cyclic, yes or no. So they had to do a very accurate numerical integration of this nonlinear system. And here you see for different methods, as a function of the step size h, what the estimated error was. And you see an Euler method, a Runge-Kutta, a 5th and a 6th order Runge-Kutta. You see this behavior like, Oh yeah, when the step size goes down, the error goes down, and yeah, there's a different scaling here. So this is 1 unit, so 2 hokjes is 1 unit here, and one hook here is 2 units. So you do have to do 1 on 4 to get 1. So I expect the slope here to be 1, right? Because it's a log-log scale, and it's h to the order of the error is h. So with a minus, so it's if the h goes down, so it should be 1, and that's pretty okay. If you go 4 forward, then it's 1 up. So it's approximately 1. And then you see for a 4th order, that's these circles. This is, I bet you, of course, that's 4, right? Because it's the 2 hokjes, one up, one forward. So that order is 4. That's pretty good. And then higher order schemes, you see that same higher order. But this is the most interesting part, of course. You hope to diminish your error until some wanted number. But you see that around this area, the systems, they cannot perform better. You hit this problem of roundoff. So always when you do this global error estimate, you have to do this step refinement and just plot them on this log-log scale and see, am I not hitting my roundoff problems? Can you solve the roundoff problems? How would you solve that? A better computer, maybe use a better computer language where the word length is larger. Instead of a double precision, use triple precision or quadruple precision, or even I think in MATLAB there is a variable precision arithmetic, VPA. So then you can say, oh, I want to have 24 digits accuracy. Of course it comes at a cost, but that is one of the solutions. Okay, see you all next week.